Hello everybody, welcome to the Ultimate Physics Channel. The topic of today's video is the photoelectric effect. The photoelectric effect is a phenomenon by which when light of appropriate frequency or wavelength is incident upon a metal surface, electrons are ejected from it. Photoelectric effect was originally discovered by Heinrich Hertz in 1887 when he was studying electromagnetic waves and trying to prove Maxwell's theory of electromagnetic waves. In his experiment that was originally designed to study the electromagnetic waves, Hertz observed that when light was incident upon one of the electrodes that acted as the spark gap in his experiment, the spark was able to travel more easily across the gap when radiation was incident upon it rather than when it was not. Hertz could not immediately understand what was happening, but he spent about next 6 months or so trying to understand this effect, and he tried to publish his initial results. He couldn't spend more time on this distraction, so he continued with his original study of electromagnetic waves. Philip Lenard, who was once an assistant to Hertz, took up this problem in the year 1888 and started doing extensive studies on photoelectric effect. Among the many contributions of Lenard of photoelectric effect, he found out that the photoelectric effect was independent of the intensity of radiation that was used. Rather, it was dependent more on the frequency of radiation that was used. Lenard also confirmed that the radiation that was ejected by the cathode, as it was originally thought, that cathode rays in fact, which were being extensively studied by J.J. Thomson and others. And he also confirmed that the charge on these rays were in fact negative, and these rays must be the same rays as those observed by J.J. Thomson in his experiment. Philip Lenard received the 1905 Nobel Prize in Physics for his contribution to this and other problems. His Nobel citation, in fact, did not explicitly mention photoelectric effect. Rather, it mentioned the cathode rays as his contribution. But one can easily infer that this was the first prize of the 3 Nobel Prizes that were awarded to the topic of photoelectric effect. Let us now proceed on to discuss the experimental setup of the photoelectric effect. This is the schematic diagram of the experimental setup. In an evacuated quartz tube, there are a pair of electrodes, the cathode and the anode, which are basically metals, and the cathode acts as the emitter of the electrons and the anode the collector. A voltmeter is connected to measure the potential difference between the cathode and the anode, and an ammeter and the battery complete the circuit. The tube is evacuated to avoid any interaction of electrons with the air molecules that would otherwise be filling up the tube. When there is a potential difference between the cathode and the anode, the electrons travel from the cathode to the anode, and this constitutes a current in the circuit. As the potential is increased, more and more electrons make it to the anode, and at a certain point, all the electrons are able to reach the anode, and the current reaches a maximum value in the circuit. When the applied voltage is negative, the electrons are stopped from moving towards the anode, and only the most energetic electrons are able to reach the anode. As the potential is increased and made more and more negative, even the most energetic electrons can be stopped from reaching the anode, and the current in the circuit becomes zero. The negative potential that is required to stop even the most energetic electrons, or those electrons that have the maximum kinetic energy, This potential is called as the stopping potential. Two important observations can be made in this experiment. The first one is the rate of flow of charge across the electrodes. That forms a current in the circuit, so that can be easily measured using this ammeter. The current that flows across the circuit is called as a photocurrent, and that can be measured from the ammeter. The next important observation that can be made is the maximum kinetic energy of the photoelectrons. The maximum kinetic energy of the photoelectrons is related to the, as I already mentioned, the applied negative potential. Let us try to understand how maximum kinetic energy can be measured in this experiment. The electrons in the metal surface have different binding energies. Some electrons could be loosely bound and some other electrons could be tightly bound. Now, when light is incident upon the metal surface, those electrons that are loosely bound are the ones that come out with maximum kinetic energy, and those electrons that are originally tightly bound have lesser energy compared to this maximum kinetic energy. When the negative voltage is applied, these electrons are stopped from reaching the anode, and as this negative potential is increased further, even the most energetic electrons can be stopped. And therefore, if a potential difference, let's say of del V is applied between the cathode and the anode, then this being a negative quantity and the charge of the electron being another negative quantity, we can say that the resulting potential barrier, which can be written as, let's say U is equal to a product of these two quantities. So basically that is a positive quantity. So the potential energy barrier is a positive quantity in this case, and this acts as a definite potential barrier for the propagation of electrons across the electrodes. And since there is a positive potential barrier for the propagation of electrons across the electrodes, the maximum kinetic energy of the electrons, let's call that as K max, that is connected to using this equation. You can write that, right? Because we've seen already that the potential parity is related to the product of the charge and the potential difference across the electrodes. And when del V becomes Vs, that is the stopping potential, at that point, even the electrons with maximum kinetic energy can be stopped. So even the most energetic electrons can be stopped using the potential, a negative potential of del V is equal to Vs. And therefore, we can write this equation. Now let us discuss some of the interesting observations that were made in this experiment. Now let us discuss some of the key observations that can be made in this experiment. The first observation pertains to the dependence on frequency. That is, the photoelectric effect depends upon the frequency of radiation that is used rather than on the intensity of radiation. That is, no matter what intensity of radiation we use, however high may be the intensity, as long as the frequency of radiation that is used is lower than the threshold frequency, let us call that FTH, that is a threshold frequency, photoelectric effect will not take place. That is, if you use a radiation whose frequency is less than this value, no matter what intensity of radiation is used, no photoelectric effect will take place. The second observation pertains to the independence of the maximum kinetic energy of the photoelectric electrons on the intensity of radiation used. That is, however high may be the intensity that is used, the kinetic energy, the maximum kinetic energy of the photoelectrons that are ejected does not depend upon the intensity of radiation. The third important observation is there is no time delay between the illumination of the metal surface with light and the ejection of electrons from it. These are the three important observations, and let us discuss these observations in some detail with the help of some plots. if we plot the current versus the applied potential between the electrodes, let's call that V, and the current as I, small I here. As long as the applied potential is positive, from a small value of current, the current goes to a maximum value. As the applied potential is 0, even then there is a small amount of current in the circuit due to the illumination of the metal surface by light. Small number of photoelectrons with high kinetic energy, that is those electrons that are loosely bound to the metal surface, and on illumination of light they get ejected from the metal surface and they travel with maximum kinetic energy towards the anode, and that constitutes some photocurrent in the circuit. And this value of current is, let us call that I max, that is a maximum value of current as it reaches the saturation point here. From a small value it slightly increases and reaches a saturation point. As the voltage changed, polarity of the voltage is changed to negative voltage, then as it becomes more and more negative, at a particular point which is called as a stopping potential, there is no longer any photocurrent in the circuit. That means even the electrons with maximum kinetic energy, that is the most energetic electrons, could be stopped with this potential, that is Vs. Now for a different intensity of the incident radiation, the stopping potential does not change. If the intensity is increased, there is a small change in the photocurrent in the circuit, but the stopping potential remains the same. So it is independent of the intensity of radiation that is used. So let us say that first intensity is I1 and the second one is I2. Here let us say that I2 is greater than I1. A small change in the maximum current as well as the photocurrent here. A general trend of the curve, there is a small difference, but the stopping potential is the same. So the stopping potential, which is related to the maximum kinetic energy of the photoelectron, is independent of the intensity. So that is what we are able to see as an observation here. And the current variation with intensity is a linear dependence. So we can see that if I plot the maximum current and the intensity of radiation, the trend is a linear one. So we can see that there is a linear dependence. That means as the intensity is increased, maximum current also linearly increases. So that is brought out by this particular plot. Another important observation that we can understand is again through a plot between the current and the voltage, applied voltage or potential. In this case, if the frequency of radiation that is used to illuminate the metal surface, if that is varied, we get, let's say, this. So these are for different frequencies. Let us call that F2 and F1 as the two frequencies that are used here. So F2 is greater than F1. Here we can clearly see that the stopping potentials are different for different frequencies of the incident radiation. The first one is F, let's call that stopping potential for F1. So Vs F1 and Vs F2 as the different stopping potentials for two different frequencies, where of course F2 is greater than F1. So for a radiation of higher frequency, we have a higher stopping potential. That means the kinetic energy is dependent, the maximum kinetic energy of the photoelectrons is dependent upon the frequency of the radiation used. Suppose if we use a frequency equal to the threshold frequency, that means this is F is equal to FTH, the threshold frequency. Then you can clearly see that the stopping potential is 0. That means it is obvious that when you use the right frequency, that is exactly that is the frequency that is exactly equal to the threshold frequency, then even a potential of 0 volt is able to stop the um, most energetic electrons. Now, if of course the frequency is less than the threshold frequency, there is no photocurrent in the circuit, so the current is simply a flat line, that is 0. This is the observation. Now let us proceed to discuss the classical theory of photoelectric effect and what it tells about these observations. Now let us discuss some of the important predictions of the classical theory about the photoelectric effect. The first one pertains to the dependency of the photoelectric effect on the intensity of radiation used. That is, the maximum kinetic energy of the photoelectrons should depend upon the intensity of radiation. That is a prediction of the classical theory. Classically, the intensity of radiation is linked to the energy of the, let us say, the photoelectrons, or the kinetic energy, or maximum kinetic energy. And this intensity, we know, is proportional to the square of the electric component, magnitude of the electric component of the electromagnetic wave. Let us call that capital E. And since there is a direct relationship, one expects classically that the kinetic energy of the photoelectrons must increase as the intensity of radiation is increased. But this is not actually observed in the experiment. The kinetic energy does not depend on the intensity of the radiation used. The maximum photocurrent is dependent upon the intensity of radiation used, but not the energy of the photoelectrons themselves. So that is the classical prediction regarding the photoelectric, the first prediction that we discussed here. The next important classical prediction is that there should be no threshold frequency. So how frequency comes into picture could not be classically understood. Intensity of the radiation used is high enough, is decent enough, then there should be emission of photoelectrons. But why there should be a threshold frequency cannot be understood classically. The third important classical prediction regarding the photoelectric effect is the significant time delay between the incidence of light onto the metal surface and ejection of electrons from it. Classical theory tells us that if the electron is confined to an atom in the metal surface, and then if the area that is exposed to the radiation is taken to be the cross-sectional area of the atom, then when light is incident upon it, a rough calculation will tell us that the ejection of photoelectrons should be delayed by at least a few seconds. But the experiment shows that there is no time delay, and therefore all the predictions, these predictions that are made by classical theory, is not experimentally observed, and therefore these three predictions can be considered as failures of the classical theory regarding the photoelectric effect. Let us now proceed to discuss how quantum theory makes all the right predictions regarding the photoelectric effect. Let us discuss the quantum theory of photoelectric effect, or simply the photoelectric theory as it is called now. Albert Einstein in 1905 made a significant contribution to the photoelectric effect by proposing a theory which is now called as the quantum theory of photoelectric effect. Following the work of Max Planck in 1900 and his proposal of the quantum theory of radiation to solve the blackbody radiation problem, Einstein drew upon the idea of quantization and took it one step further ahead of Max Planck. This Max Planck's theory proposed that the radiation exchange or the energy exchange between systems occurs in terms of quantized packets of energy now called as photons, or quanta of radiation. Einstein took it one step further ahead, and he proposed that not only the radiation that is exchanged between systems is quantized, but also the radiation or the energy itself is quantized. That is, the energy or radiation itself is made up of discrete bundles of energy or packets of energy, now called as photons, which are basically quanta of radiation. So this is a significant advancement of thought in the way we understand physical systems. The electromagnetic theory predicts that the energy is entirely carried by the wave and is distributed uniformly throughout the wavefront, whereas Einstein's photoelectric theory significantly differs from it in terms of the distribution of energy as small packets of energy within the wave. So this is a very important distinction between the classical thought process and the quantum way of thinking, right? So that is brought out beautifully in the quantum theory of photoelectric effect proposed by Einstein. Einstein proceeded to use Planck's idea and called that this quanta of radiation or energy has an energy equal to E is equal to hf, where h is the Planck's constant and f is the frequency of radiation. And this can be expressed in terms of the wavelength of the radiation also as E is equal to hc over lambda, where c is the speed of light. He proposed that these photons that make up the radiation or light, they must travel with the speed of light. And if they must travel with the speed of light, they must be massless objects or massless particles. So one can write, using the relativistic equations, the momentum for these photons as E over c, right? And that would imply that the photon momentum is h over lambda. If the photons would have mass and they would still travel, let's say, with the speed of light, then their energy and momentum would be infinite, which is not allowed, and therefore it is obvious that the photons do not have any mass. Not only the photons do not carry any mass, the rest energy of the photons is also zero. That is, E is equal to mc square, the famous equation, relativistic equation, must also be zero for photon. Einstein, in his photoelectric theory, further went on to propose that each photoelectron is emitted as a result of the exchange of energy between a photon and a single electron, which takes up the energy and uses excess energy as the kinetic energy to get out of the metal and travel. And therefore, he proposed this famous photoelectric equation, which is the maximum kinetic energy, let's call that K max, that must be equal to the energy of the photon that is supplied minus the work function of the metal phi. So the difference in these two energies, it manifests as the maximum kinetic energy of the photoelectron. And this quantity, which is the work function of the metal, it varies from a metal to another metal. That is the amount of energy, the minimum amount of energy that is required for an electron in a metal to break free from the metal surface. And this energy is typically, for most metals, nearly half as much as the ionization energy. For example, if you take the case of cesium, for example, the ionization energy is about 3.9 electron volts, whereas the work function phi is about 1.9 electron volts. So it's nearly half compared to the ionization energy, which is the energy that is required by an electron to break free from a free atom. And this work function depends upon the threshold frequency that we discussed earlier. Therefore, we can write that phi is equal to hf/dh, that is Planck's constant times the threshold frequency gives the work function. We can write this as Kmax is equal to hf minus hf threshold, or hf minus f threshold is Kmax, right? And we know that this Kmax is linked to the stopping potential. As per our discussion, we have shown this to be true, and therefore we can extend this to this as HF minus HFTH. Is another form of the photoelectric equation, Einstein's photoelectric equation. So this equation, Einstein's photoelectric equation, is of the form of a straight line equation. Let's continue to write it here. Here, this is of the form y is equal to mx plus c, which is a straight line equation. That is, here our y is UAS. So if I plot this curve, this can be called as the stopping potential energy. Vs is the stopping potential. Then I multiply it with the charge of the electron, that becomes a potential energy. So it is, let us say, stopping potential energy on the y-axis, and the frequency on the x-axis. So we plot this curve, we would expect a straight line, right? Because this represents a straight line equation. So we will see a straight line. And this x-intercept on the positive x-axis is the threshold frequency, value of the threshold frequency, and if we extend this onto the negative y-axis, what we would get is the work function of the metal. Based on these discussions, it is possible to see that Einstein's photoelectric theory is able to explain all the observations that is made in the photoelectric effect, namely the dependence of the kinetic energy on the frequency of the radiation used, and the equation does not have intensity anywhere, and therefore we can clearly see that why the maximum kinetic energy should be independent of the intensity of radiation used. And regarding the time delay also, we can clearly see that there should be no time delay between the illumination of the metal surface by light and the ejection of electrons from it, and thus Einstein's photoelectric theory could successfully explain all the observations made in the photoelectric effect, and could be verily considered as a very successful theory of photoelectric effect. But then scientists of the day were skeptical about the quantum theory itself, and more so about the photoelectric theory as well. Therefore, Robert Millikan set out to do a series of experiments on photoelectric effect in the hope of proving Einstein's or disproving Einstein's photoelectric theory itself. 1950, Millikan carried out extensive studies by taking different metals as cathodes and performing this experiment, and he was able to clearly get these straight lines, that is frequency versus the stopping potential energy plots he was able to get, and for different metal surfaces, he was able to get parallel straight lines, each giving different values of the work functions for different metals on the negative y-axis, and different threshold frequencies on the x-axis, and the slope of this curve is the Planck's constant, and Millikan was able to get exactly the same value within the allowed limits of errors, value as that was obtained by Max Planck himself in his quantum theory of radiation for the blackbody problem. And these two values, since these two values agreed, the scientific world started accepting Einstein's photoelectric theory in particular and quantum theory in general more readily later on. And Einstein was awarded the 1921 Nobel Prize in Physics for his work on photoelectric effect, among other things. And Millikan was awarded the 1923 Nobel Prize, the third in the series of Nobel Prizes for the photoelectric effect. Of course, Millikan also had other contributions, the measurement of charge to mass ratio of electrons and so on and so forth. Let us now quickly discuss some of the applications of the photoelectric effect. Photomultiplier tubes is one of the important applications. Photomultiplier tubes are devices that are capable of amplifying a small light signal into a large electrical signal. Particularly in several neutrino detection experiments, hundreds of photomultiplier tubes are used. Some of these neutrino detection experiments include the Kamiokande in Japan, the Sudbury Neutrino Observatory, and the successor to it, SNO Plus, and the ice cube neutrino detection experiments in the South Pole, where the extremely sensitive photomultiplier tubes come in handy to detect neutrino events. Photoelectric cells which are light activated devices basically that have several applications. For example, intrusion systems, burglar alarms can be thought of as some of the cases where photoelectric cells are employed. Solar panels, which have wide applications, is based on the photoelectric effect. Though the material is a semiconducting material, the working principle is the photoelectric effect, where the light energy is converted into electrical energy and power is generated out of sunlight. That is the basis of the solar panel, which is photoelectric effect basically. And then photodetectors in several devices such as cameras, for example, they also work based on the photoelectric effect. Last but not the least, one can even think of human eye as a light detecting system that works based on the principle of photoelectric effect. As light photons impinge the human eye and it is detected, some kind of electrical signals must be traveling to our brains, telling us what we are seeing, and therefore it can be also thought of as an extension of the photoelectric effect basically. These are really some of the very limited number of applications that I have been able to cover here, but one can explore a large number of applications that are present for photoelectric effect. The importance of photoelectric theory in the development of quantum mechanics and in the understanding of the fundamental nature of light cannot be overemphasized. That brings us to the conclusion of this video. Hope to catch up with you soon on another interesting video. Until then, it's bye from me. Thank you.